Hello everyone. In this lecture we are going to see the derivation of log mean temperature difference for parallel flow heat exchangers. So first I will draw the diagram for parallel flow, that is how the flow occurs inside a heat exchanger, and then we will have a derivation, step-by-step derivation for LMTD. Now, I'll teach you how to draw the flow diagram. So this is the inlet, and here we have the outlet. So in, and this is the out. It doesn't matter which side is the in and which side is out for a parallel flow heat exchanger. Anyways, you are going to get the same value of LMTD only. Now we have two fluids, that is the hot fluid and the cold fluid. The hot fluid is at higher temperature, and while at the exit it is at a lower temperature. So you can see the curve like this. Right? So here I will name it as TH in and this is TH out. Now we have the cold fluid. Since it is a parallel flow, both the fluids will be flowing in the same direction only. So again we have the cold fluid inlet here only. So it will start here. Initially it will be at low temperature. As it propagates, it will exchange heat with the hot fluid and it will gain temperature, right? So you can see here. So this is your TC inlet and this is TC outlet, right? Now I am going to mark 2 points. This is the first point and this is the second point. The difference between these 2 points is named as delta T1. Clear? Likewise, these 2 points from here to here, this difference is delta T2. Okay. Now, what is the importance of log mean temperature difference, or what is log mean temperature difference, we will see. See, now the fluid is propagating through this pipe from inlet to outlet. At the inlet, you notice that the difference in temperature is delta T1. At the outlet, the difference in temperature is delta T2. Somewhere in the mid, I am going to take the temperature. What will be the value? We don't know. Is it okay if we take the arithmetic mean of these two values, that is delta T1 plus delta T2 divided by 2. Is it okay if we take this as a value and calculate the heat transfer using this formula, that is U into A delta T mean? Is it okay if I substitute this one here? No, it is definitely not okay, because this value, that is the arithmetic mean, is not going to give you an idea about this exponential degradation in temperature. In order to capture exactly what the degradation is here along the length of the pipe, it is always essential to calculate LMTD only. So that is why we are worried about the derivation of LMTD. Okay. Right. Now I am taking a small section. So let this be a section. Right. So this section, let it be AS. Okay, surface area is AS and heat is propagating like this. Okay, and let the heat be del Q dot. Now you can see the difference in temperature for the small section from here to here. Let this be called as DTH. Likewise, from here to here, this difference is DTC. I hope it is clear. Okay, now finding out the heat transfer for the small section. Right? So del Q is minus H CPH DTH. Why it is minus, I will tell you. Heat is lost by the hot fluid. So obviously the outer one will be lesser than the inner one. So TH naught minus THI will be negative. So to remove that negative sign, so there's already, we have inserted a negative sign on the heat transfer. Now I am writing for the cold fluid. BTC. Okay, this is the first equation, this is the second equation. Now, I am going to rearrange both the equations. That is dTH I am going to keep here, and it is going to be del QH, that is heat transfer for the small section, divided by mH CPH. Likewise, dTC is going to be del Q dot divided by MC CPC. Right? And let's put it here. Now, subtracting these two equations, what will I get? dTH minus dTC equal to del Q is common, so I will write 1 by mH CPH minus 1 by MC CPC. I hope it is clear till this. Right? Now, already there is a negative sign, right? So I am taking this outside. So this is going to be, till this step we have derived, that is dH minus dTC and del Q in terms of U and DAS. Now I am going to substitute this equation, that is this value of dQ in this place. So we will be getting the same left hand side, no change. In the place of del Q, I am going to use this one, right? So minus U TH minus TC into DAS, and inside the brackets whatever is already present has come down. Right? Now again rearranging this equation, that is I am bringing this to the left hand side, d of TH minus TC divided by TH minus TC, and on the right hand side you will have this minus U term, DAS term, and whatever in the brackets. In the brackets we have this heat capacity rate, right? That is 1 by mH CPH plus 1 by MC CPC that we have. Now integrating this equation between the inlet and the outlet. So when I say inlet and outlet, your value is going to be like this. That is ln of TH outlet minus TC outlet divided by TH inlet minus TC inlet, and that is equal to minus U. This DAS will become AS itself. And inside the brackets we have the same term, so I am not writing it again and again. Fine, till this step we are done. We have the general equation for heat transfer, that is Q equals mH CPH TH inlet minus TH outlet. Likewise for cold fluid, MC CPC TC outlet minus TC inlet, right? Now in this equation we do not know the value of mH CPH and MC CPC, right? So I am going to use this equation over here at this last equation. So this we won't need. Now there it is 1 by mH CPH is going to be 1 by Q THI minus TH naught. Likewise 1 by, this is mH, mH CPH. It is MC CPC. We have the general equation for heat transfer, that is Q equals mH CPH TH inlet minus TH outlet. Likewise for cold fluid, MC CPC TC outlet minus TC inlet, right? Now in this equation we do not know the value of mH CPH and MC CPC, right? So I am going to use this equation over here at this last equation. So this we won't need. Now there it is 1 by mH CPH is going to be 1 by Q THI minus TH naught. Likewise 1 by, this is mH, mH CPH. It is MC CPC, that is going to be again 1 by Q Tc naught minus Tci. So this is our final equation, right? I'm going to substitute the values here and here. So ln Th naught minus Tc naught divided by Thi minus Tci is going to be minus UAS. This was earlier 1 by ms Cph, right? So I will write this value. That is Thi minus Th naught minus this one, Tc naught minus Tci, right? And what is left? This q is actually left. So this is your simplified equation. In most of the textbooks, immediately after this equation, they have given you the final equation stating that some rearrangements are done. I'll show you what are those rearrangements also in detail. Okay. Now you see Th naught minus Tc naught. What is it? Look at this figure, back to the figure. Th naught minus Tc naught is delta T2, right? So it is ln delta T2 divided by, what is this? Th inlet minus Tc inlet. So Th inlet minus Tc inlet is delta T1. Delta T1. That is equal to minus UAS by Q. And look at this, Thi minus Th naught. We don't have any temperature difference to represent this Hi and H naught. Rather, we have only for Hi and Ci. So what I'm going to do, I will take this Thi and I'll take this Tci, right? So what will I get? Thi minus Tci minus, we are left with Th naught and Tc naught, right? So Th naught and Tc naught. This is what we are left with. I am erasing the above two lines. Now again this Thi minus Tci is delta T1, right? So left hand side remains the same. Minus UAS by Q, and here it is going to be Thi minus Tci is delta T1 and minus this is delta T2. Is it clear? Now I am going to remove this negative sign. So the ln will get the inverse, right? So it will be ln delta T1 by delta T2, the other way of writing. Okay, US by Q into delta T1 minus delta T2. Fine. So all this is not needed. Okay. Now this Q, bringing it here, QAS delta T1 minus delta T2 divided by the ln value T1 by T2. That's all. Now this one, this is called as the log mean temperature difference. Got it? So it is for arriving this one only. We have started right from the heat transfer equation. Okay. So it is just I'll recollect. It is always not wise to use the arithmetic mean temperature difference because this exponential decrease will not be exactly captured. For it to be exactly captured, we have to use this equation only. In cases where the difference between this delta T1 and delta T2 is less than 40 degrees Celsius, okay, the heat transfer that you attain will not show much variation, then you go for arithmetic mean difference or LMTD. But when this is greater, that is greater than 40 degrees Celsius, you will see a drastic change in the heat transfer values. Okay, and always the value that you arrive, that is by arithmetic method, will give you high value, so that it is giving you a wrong implication that the heat transfer is very high, but actually the heat exchanger that you have designed for these inlet outlet conditions will not give such high value. Okay, so it is actually a wrong interpretation only. This class we have seen for parallel flow. So the same can be extended for counter flow. You can just try it. If you have any doubts, please mail me. When we are going to use it for a cross flow or a multi-pass shell type heat exchanger, there is something called as correction factor that has to be included. That we can see in the next class. I hope this lecture is clear to you. Thanks for watching.